Um, okay, so for two people here and two people not here, Sarah and Carly, you better be watching. Time to actually get numerical for us numerical PDEs class. Now that we're almost halfway through the semester. Okay, and so there's many different types of numerical methods for PDEs. So I'll start off with the most straightforward one that really works with basically definition of derivative to replace whatever partial derivatives we have in the PDE. So those are called, so this is section 2.1 in the notes. Finite difference or FD methods. Okay. So at first, and this is actually what I'll show you today, a very simple equation. So 1D Poisson's equation. Okay, well, Cameron's just putting you guys in the spot. What is Poisson's equation?
We just did that last week. Something equal to F.
Yeah, there's an F on the
to the
right side.
Was it UTT?
So really we've seen, well, Laplace and Poisson are basically the same things, except only Poisson has the F, whereas Laplace is 0 on the right side. Then there's heat equation and wave equation, but this is the one that does not depend on time. Well, the heat equation and wave equation do. You have a guess?
Negative gradient squared.
Oh yeah, it is that symbol. Yeah, so yeah, that. Well, this symbol, gradient squared, or that's how we write it.
Mm-hmm.
What do we call that? Starts with an L.
Laplace.
Yes, good. Laplacian. So also written this way. But to see if either of you recall anything what the Laplacian is, we are in one dimension, so our typical spatial variables, x, y, z, etc., we only have x. So what would the Laplacian be? So what partial derivatives would I fill in there?
X. Two of them?
Yes, two of
Two
them.
of them.
Okay. UXX, yeah, so minus UXX equals F. Okay, so Poisson equation reduced to 1D is just that. Now, the irony is, this is allegedly a numerical PDEs class, but you can say, well, it's really an ODE, because U depends on only one variable, X. But whatever. But yeah, what I described here can be applied or generalized to higher dimension in a straightforward manner. Plus, we are going to include time later. Now, I have to specify various things about this problem to nail down a unique solution. There won't be any kind of initial condition for this because we don't have time. What kind of condition will we have instead? Boundary conditions. If we are on a finite, or actually, if our domain is not the whole real line. Like before I was doing Cauchy problems where the domain was the entire real line, but we will have a bounded interval, bounded domain in this case. So we're just going to solve it on the interval 0 to 1. Okay. And so then we need boundary conditions. And I'm actually going to talk about different boundary conditions. So there's, I brought this before, but I want to have everything in one place. So Dirichlet would be u of 0 equals something, like some value u naught, u of 1 equals something else. So in other words, we're specifying the value of a solution at the two boundary points, x equals 0, x equals 1. Another possibility is Neumann, where it's specified the first derivative. Instead of a solution. That would automatically mean that the solution is not unique because, well, actually for Laplace's equation, I could add a constant to the solution because that constant would not be not affect the boundary conditions. Or, depending on f, a solution might not exist, so we have to be careful about that. And then, this one won't really come up in this chapter, but in a later chapter will come up. And I deal with it a lot. Periodic. So we specify a wraparound. That's the boundary values must be equal. Typically, it also means that the same must apply to the first derivative for periodicity. You can also mix them, like you might have Dirichlet at one boundary point and Neumann at the other. Or you could have a linear combination of them. Like I could have A times U plus B times UX at one boundary, and then at the other boundary, different constants combining them. So these are called mixed boundary conditions, also known as Robin boundary conditions. Well, it's been a real achievement to slap his name on that one. Okay. So what we're going to do here is go from this PDE on this domain with whatever boundary conditions we have and through a process called spatial discretization, we're going to obtain a system of linear equations. Often when it's generic, it's referred to as an AX equals B problem, but I figured I'd give different names because U would refer to U of X and F would be based on the function F of X. And once we have that system of equations, we can just solve that by whatever means. Gaussian elimination. Later we'll learn about iterative methods. The matrix A should be SPD, symmetric, positive, definite, which is the reason for that is the operator minus Laplacian is self-adjoint and positive definite, which is this is an analog of symmetric positive definite. So we're talking about matrices in this case and linear operators in the other case. So when a linear operator is self-adjoint, that corresponds to a symmetric matrix. Positive definite has the same meaning for both. It means the eigenvalues are positive. Actually, when you have Neumann boundary conditions, it might be positive semi-definite, meaning the eigenvalues are non-negative instead of positive. But I'm not going to get too hung up on that right now. Okay. we have a system of equations like this that is known to be symmetric, positive, definite, what's the faster way to solve it instead of Gaussian elimination? Anybody?
It's been a while since-
Okay. Yeah, I know. I just thought I'd take a chance. Cholesky. The Cholesky. I saw that.
No,
Yeah. Well, it might have been one in a class that you've taken. I don't know. You saw it last. Oh, yeah. No, it was the spring before last. It's been a year and a half. But okay, so you're excused. You did know it though, didn't you? Okay. All right. So what I need to show you is how do we get from here to here? How do we set up the system? As far as the particulars of solving it, that's a later chapter. But right now it's about setting it up, and it includes taking into account whatever boundary conditions you've chosen. I'll start with these, and I'll talk about the other ones later. Okay. So we need a way of describing that second partial derivative with respect to x. But I need to talk about spatial discretization in general. Because if you're solving the PDE analytically, like I've been talking about really all semester long, we're solving for a function u of x. Like the PDEs I've been solving lately, we have a formula for this function u of x or u of xt. And now we're not going to have that anymore. So our solution is a vector u that has n elements. Okay. Now, for now, I'm going to assume Dirichlet boundary conditions. So what that means is, at the endpoints, x equals 0, x equals 1. So here's our domain. So at these points, we know the solution. It's whatever boundary conditions say they are. In fact, I'll be more specific. I'm going to assume that the boundary values are 0. Because for a case where they're non-zero, we can actually reduce it to this case and deal with it that way. Okay, so at the endpoints, we know these values are 0, so we do not need to include them in here. So what we have is, in this vector, our values of u of x at interior points. So u1 is the value at x1, u2 is the value at x2, and etc. un is the value at xn. And they have to be in the interior. So I'm going to label them here. x1, x2, up to xn. Okay. So then we have some spacing in between. So I'm going to label the spacing. Let's call this H0, H1, H2, up to Hn. So Hi is equal to xi plus 1 minus xi. Most of the time, we will assume uniform spacing, but I don't want to rope myself into that just yet. Now, before I continue, one very important point to make is the choice of boundary conditions affects which points are the unknowns. So, for example, suppose instead of Dirichlet boundary conditions, I impose Neumann boundary conditions. Well, that means that x equals 0 and x equals 1.
We don't know.
Right, we don't know those values, so they are lumped in. We now have a total of n plus 2 unknowns instead of n. Now, the boundary conditions will help us set up the equations, but it means more unknowns than in the Dirichlet case. So, actually, what I'd probably do in that case is still like number them from x0 up to xn over here, and call that like so. N almost always refers to either a number of points if you're starting from 1, or a number of points plus 1 if you're starting from 0. If it was periodic, I would include this one, but not this one because it matches. So when you're setting up your spatial discretization, determining okay, which points are known, which are unknowns, you have to think about the boundary conditions. So that comes into play immediately. So for now, we'll just stick with Dirichlet and say only the interior points are the unknowns. Okay.
What about the Robin? What would you do there? Is it just going to depend on the problem?
Yeah, it depends on, basically Neumann, if you have, for instance, if there's any Neumann in there, you got to include the endpoints. Mm-hmm. If it's pure Dirichlet, you don't. Okay. And one example I'll show later has Dirichlet at this end and Neumann at this end. So we include that, not that. Boundary conditions are a real pain. They complicate everything. Okay. All right, questions so far about the setup here? So at each of these points, n points, n unknowns, so it means I need n equations. So we need to let's try minus uxx is equal to f at each xi. We're going to examine uxx evaluated at xi is equal to f at xi. Now, the PDE is linear. So I want to get from this a linear equation. So it must be linear in all of the unknowns, u1, u2, up to un. So now the right side is no problem. F is given. So I can plug in xi into f and get my right-hand side value. So a right-hand side, not a problem. What I need to do is express this derivative in terms of these unknowns in such a way that these are involved in a linear manner. In other words, they're multiplied by constants, added together, and that's it. I can't have any funny functions of these, like squaring them or whatever, because that would be a nonlinear equation. And it makes sense that it would be a linear equation because differentiation is linear. The derivative of a sum is the sum of derivatives. If you multiply a function by a constant, it multiplies a derivative by that constant. So a linear operator should be possible to approximate by a linear function of these unknowns. So an approximation of this form. uxx at xi is approximately equal to a sum, well, minus, because it comes from the equation. Sorry, that should, well, yeah. Forgot the minus. So I have aij uj. So I'm saying that second derivative at each point xi is approximately a linear combination of all the unknowns. But this, and this has to be equal to fi. So this defines my system of linear equations right here. This is a formula for matrix vector multiplication. So once I find the coefficients aij, then I have my system. The au, I erased it. Au is equal to f. So these numbers right here, aij, they make up the ith row of A. So all I got to do is figure this out for each row. And then I have my system. Okay, now, I've given no indication whatsoever on how we're going to find those aij. So we're like completely lost in the woods on this one. But by coming up with like imposing some parameters on how we can try to find these coefficients, we can actually get somewhere. Okay. So, what we do is use a Taylor expansion. Okay. Around xi. So, the reason why I chose xi is because we're evaluating a derivative at xi. So we're so in order to get the coefficients that we need in row I of our matrix, we need to do a Taylor expansion around that point. So what would that mean? So u of xj, so this is whatever index we have, is equal to u of xi plus ux at xi times the difference in x values plus 1/2 uxx at xi. This is important because, dang it, that's exactly what we want. Okay. Times xj minus xi squared plus, and we will keep going from there. Okay, actually, I'll do one more term. Third derivative with 3 factorial xj minus xi cubed, and so on. Okay. Now here's where things begin to get really messy. So what I'm going to do now is, so this is approximated by uj. So what I'm going to do is, if you look over there, I have this sum, aij uj. So now I'm going to take this Taylor expansion and substitute it for uj. So I have so I'm going to have ui plus, and I'm going to use a shorthand here, uxi, so it's du dx at xi times xj minus xi plus 1/2 uxx I plus 1/6 uxxx times xj minus xi cubed. Okay, and so on. And all of that must equal minus uxx at xi. The next thing I'm going to do is group terms differently, because right now I have aij times this whole mess. But what I really want to do is now is group all the terms, the many terms of summation, by the u's, ui, uxi, uxxi, and so forth. So what I have is because notice, ui, uxi, uxxi, all that, they don't depend on j, only I can pull them out of the sum. So I'm going to have ui aij, sum of aij. That counts for this part. Then I'm going to have uxi times the sum xj minus xi aij. And then uxxi times, actually, I'll leave a 1/2 in the sum. So the sum 1/2 xj minus xi squared aij. And I know I had this term in here, but I'm just going to dot it. And that has to equal minus uxx and xi. Questions about how I got to here?
Is there a particular rhyme or reason why, like, you went out to the third term up there earlier? You decided to, and then like.
You're gonna find out in a second.
Okay.
Okay. Now, because I want this whole thing on the left side to equal minus uxx, that means any terms on the left side involving things other than uxx, like other orders of derivative, have to go away. In other words, I need this to be 0. So that way there's no involvement of just plain old ui. I need this to also equal 0. So that there's no uxi either. What about this? What do I need that to be?
XI.
Oh. Oh, I see. Because you were looking at this, right?
Right.
Okay. I'm sorry. If I use the same notation, that's also that.
Oh,
It's not multiplication, it's function evaluation. Okay. Now try again. What do I need that thing in brackets to equal?
-1.
Yes. Okay. If I had brought the other one down, the 16uxxx, and done the whole spiel with that also, what would I need that to be?
I'm sorry. Can you say it again?
Yeah, I missed what you said.
I was right.
If I brought this down, that down, that down, I did not bring this down, involving a third derivative, but if I had to give a similar expression,
0.
yes, it has to be 0. Everything has to be 0, except that. Because that's the only derivative I want. Okay. And yeah, here I stopped. I never went past the third derivative. If I had, all of those would have to be 0 too. Okay. Okay. Now, so what I have now is, yes, so now I really have a system of equations for the AIJs. I've specified 3 of them so far. That sum equals 0. This weighted sum must equal 0. This sum of these coefficients must equal -1. Is anything involving xi, xj? I know those. I've specified those x values. Okay. But I could have as many equations as I want. Because by filling in more terms of a Taylor series, I just have it written down here, where all the right sides would equal 0, except for about 1. So now I have to make a choice, like, how many coefficients aij should I have in my approximation? So, because you would think that the more coefficients I include, the more accurate my approximation may be, because I'm including more terms of a Taylor series. But it also makes it more expensive to work with. So what I'm going to do here is I'm just going to make a choice of a very small number of points. I'm going to have, for each approximation of uxx, I'm only going to use 3 points. Which means I only need 3 equations. And that's actually why I didn't bring that down. Because then I realized, oh, I'm not going to need this. Okay, so in each row of my system of equations, I can approximate uxx using only 3 points. So then I'll have a 3 by 3 system of equations for each. But now the question is, which 3 should I use? I have a lot of choice there. So what I'm going to do is, for this example, I'm just going to pick something. Because I want a derivative at xi, whatever xi might be. So since I'm going to choose 3 points, the 3 points will be itself, xi, and then the 1 to the right, so it's xi plus 1, and then the 1 to the left, which would be xi minus 1. So it's going to be I minus 1, I minus 1, plus I ui, plus I plus 1, times ui plus 1. So at least each of the 3 equations I have will not have very much in them. Then I'm going to simplify things a little further. I'm going to assume equal spacing. H0, H1, H2, Hn, all equal to some uniform value H. And in fact, because it's equal spacing, I can tell you what H is. This will be important when you guys eventually do stuff in MATLAB. It's going to be the length of the interval, which is 1, because we're operating on interval 0 to 1, over n plus 1. Now, so I have those 3 equations over here, but now I need to specify what these 3 equations would be in terms of the simplifications that are made here. Okay, so I have, first, I have equation, the sum aij equals 0. So what does that mean in light of what I've just shown you here? So what I've done is I've specified that most of these are already 0. There's just going to be at most 3 that are not. So I'm going to have I minus 1 plus I plus I plus 1 must be 0. So I'm looking for my 3 coefficients. They all have to sum to 0. In fact, anytime you're approximating a derivative using this approach, you're expressing the derivative at a certain point as a linear combination of surrounding values, the sum of your coefficients is always going to be 0. And I can explain why. Because since this is my expression for my approximate derivative right here, suppose u is a constant function. So it's just some value, uniform value u. I can factor it out. And then what's left? I have u times the sum of all the a's. well, that's supposed to be 0. Therefore, the sum of the a's must be 0. So any approximation of a derivative by finite difference with these coefficients will always sum to 0. First derivative, second derivative, doesn't matter. So it's a way of checking that you've computed them right. Okay, that's the first equation. Second equation, I have a sum of xj minus xi, aij, is also 0. So what does that mean in terms of these three coefficients? Well, when j is equal to I have xi minus xi. That's already 0. So the second term in this will already be 0. So what I'm going to have is xi minus 1 minus xi, ai I minus 1, plus xi minus xi, aii, plus xi plus 1 minus xi, I plus 1, is 0. But now I can account for there being uniform spacing. So this is minus h. Because this point is to the left of this one. This is 0, that's xi minus xi. And this is going to be plus h. Well, now I can simplify that. I can divide through by h. So now I'm saying that this coefficient equals that coefficient. That's a consequence of the equal spacing, and plus the fact that it's second derivative. If it was first derivative, they'd actually be minus each other. Okay. And finally, I have this third equation over here, where the right side is minus 1. So I have 1/2 xj minus xi squared aij is equal to minus 1. So what I'm going to get out of that is, instead of minus h and h, I'm going to have those things squared. So I'm going to have 1/2 h squared aij plus 1/2 h squared, sorry, not aij, ai I minus 1, and then ai I plus 1 is equal to minus 1. Okay, so I have three equations in my three unknowns. So now I could just let's see. Yeah, I could just go ahead and work that out on paper, really. Or I can make you guys do it. Because what you could do is you can use these equations, solve for the off-diagonal entries, and then once you have those two, you can put them in here and use the fact that they sum to 0 to get to diagonal entry. Because notice AII is not involved in either of these two. Okay. And we already see that they're equal. So what this would tell me is, like, I could replace AII minus 1 with AII plus 1 and combine the like terms. So what I get is h squared ai plus 1 is equal to minus 1. So I get ai plus 1, which is already known to equal a minus 1, is equal to minus 1 over h squared. Questions about how we got this far? So with that, the last unknown, AII, what would that be? Just one equation we still have to use.
The top one.
Yeah,
And you said all of them sum to 0.
yes, that one. So now these two that are equal to minus 1 over h squared, we can fill in there and get AII, which is what?
Two over h squared.
Yes. You got that too? Okay. Yes, 2 over h squared. All right. So now I can put everything together. So the system of equations is ui I minus 1 minus, minus that plus 2ui minus the u's have only a single subscript. So ui minus 1 plus 2ui minus ui plus 1 all over h squared is equal to fi. And this holds for I equal 1, 2, up to n. So, okay. What I did was, I went here and replaced the ai minus 1, aii, the ai plus 1 with the values that we got. And that gave me my second derivative approximation, and that's my left side. And then I have fi on the right side. So this got substituted in here. These two, sorry for my hardwood report use that you're all used to. This. So I just plugged them in there, and that said, okay, that's my minus uxx part. And I set it equal to f. So questions about how this finally fell out? All make sense, kind of?
Mm-hmm.
Okay. All right. Good, because now I'm going to tell you about what I neglected. Well, actually, for most part, these equations are fine. And it turns out really all of them are correct. But there's one thing I glossed over, which I shouldn't. Because what happens when we deal with a boundary? Like when I is equal to 1, I have u0 over here, u1 and u2. u0 is not among my unknowns. But But if ui is approximation of u of xi, so u0 is value of my solution where? If you go back to my diagram where I drew out the domain.
Oh, your initial point, the starting point?
Yeah, at x equals 0. So that's my approximation of u0, but what is that? What did I specify that to be?
The boundary condition.
Boundary condition. And yes, there's a additionally boundary condition, but that's 0. I posed those homogeneous boundary conditions earlier. So we just don't include this, and it's fine. So and similarly, at the other point, at I equals n, I have un plus 1 over here. So un, which is my approximation of u of 1, is also 0. Okay, so in that case, I just don't include those points because the values are 0. But either way, they're specified. What do you think should happen to this system of equations? Because this is the correct system of equations. What if I had specified u naught to be some non-zero value? Like say u of 0 is equal to 2.
So bump everything?
Bump meaning what?
Meaning like we just start there with that value and if it's equally spaced and equally across, kick those?
Well, we're still using the same points. But let's just think about this equation. Because the idea is we want to have everything we don't know on the left side, everything we do know on the right side. So when I is equal to 1, we have this u0 here. I have to say that that's 2. So I can go ahead and fill that in. But I want to have a system of equations like matrix times u is equal to a right-hand side. So if I had to fill in a value here that I know,
what? Did multiply the other side by 2?
Yeah. Well, not multiply, but no, this term, that term moves to the other side. Yeah, so I'm gonna have a plus 2 over h squared over here. So when you have boundary terms, we like it when they're 0 because you just ignore them. But if in case they're non-zero, just move it to the other side. So it becomes, so your right-hand side is not just the right-hand side from your PDE, that function f of x. It may include boundary terms also. So that's a key point I want to make here is that your right-hand side vector for a PDE like this is right-hand side function of your PDE if you have one, and terms that arise from the boundary conditions. So your discretized system does not match your PDE exactly because there's boundary effects. All right. Okay. I just looked, it's 5:38. It's like, wow, this class is going on forever. It's supposed to be like 10 times worse for you guys. I thought, we'll be done in a few minutes. Okay. Now, so I want to show you, since this is a system linear equations involving a matrix, AU equals F, what does A look like? So A is equal to every term is a 1 over h squared, so I'm just factoring that out. So we think of how I labeled these matrix entries over here. I have AII, and then AII minus 1, and AII plus 1. So the first index refers to a row, it's row I. The second index refers to a column, because it's showing what value from u you're multiplying by. So I have these entries, at most 3 non-zero entries in every row. -1, -1, and a 2. So based on these indices that indicate where they go in the matrix, row and column, can anyone tell me, I'm such an idiot, I just gave it away. Because what does this matrix look like? And I just, one motion gave it away. Well, all right, salvage this. What goes where?
The coefficients go along the diagonal.
Which ones go in the main diagonal, right down the middle?
AI, I-1, AII,
They go in that order. So AII is the diagonal, the main diagonal. So what do I put here on the main diagonal?
Oh.
From this.
-1, 2, -1?
Yeah, they go in that order, but the diagonal is only 1 entry per row. So there's my errant finger gesture here, main diagonal, and then there's one diagonal above, it's called the super diagonal, and there's one diagonal below, that's the subdiagonal. So that leads to the 3 entries for each row. But if you look at how they're indexed, we have II, like when row and column and index are equal, that's the main diagonal. If it's I plus 1, the column is 1 to the right, that's the super diagonal. And here, I minus 1, the column is to the left, so that's the subdiagonal. But since we know what all those coefficients are, what values would go along here? Yes, 2 over h, well, I've already factored out to 1 over h squared. So yeah, we have 2's down the diagonal, and then what goes above and below?
Negative.
Yeah. Okay, so -1. Okay. Oh. Okay. So that's the matrix that we get. What do we call a matrix that has that structure? Where we have just those 3. We have main diagonal and one diagonal above and below. What's the term for that? Yes. So this is a tridiagonal matrix. There's one other thing we can say about it. There's one other adjective we could use to describe this matrix, besides it being tridiagonal. Based on pattern in the entries. Well, actually, there's more than one, but I'll take one. And it's not obvious from looking that it's positive definite, so I'm not thinking of that one.
So just symmetry.
Yes. Good. All right, so I semi-limited that one, but still good. Symmetric. Now, a positive definite matrix has to have at least positive diagonal entries, which this does. Another adjective that I've not talked about in a prior class, when you have all the entries down the diagonal the same, so all -1s, all 2's, all -1s, it's also called a Toeplitz matrix. So that has some particularly nice properties. In particular, it makes it possible to analytically figure out the eigenvalues and eigenvectors, which we don't need for this, but it's helpful elsewhere. Okay, so now we could just go ahead and solve this system of equations by the method of our choice. Since it's symmetric positive definite, like among direct methods, Cholesky would be preferable over Gaussian elimination just because it takes less time. Some iterative methods that I'll talk about later might also be preferred, especially in the case where n is large. But yeah, it's a problem that's extremely well studied. Okay. Let's see. I do want to talk about, so actually in the notes, what I've really done is kind of mash sections 2.1 and 2.2 together, because 2.1 is about finite difference in general, but I sort of jumped direct to Poisson's equation just to make things more concrete. I do want to take time to talk about Neumann boundary conditions, but real quick, suppose the boundary conditions were periodic instead of Dirichlet. So then what would happen is, like when you're at your left boundary, like suppose this is a point on the left boundary, and this is a point to the right. This is a point to the left, but when you're going to the left, it's outside your domain. You're not allowed to have that. But when it's periodic, it wraps around to be the point. All right. Yeah. So as a result, if I did the whole process with periodic instead of Dirichlet, I'd have a -1 here and here. In other words, this subdiagonal wraps around to go up here, and then this superdiagonal wraps around to include that. And that's called a circulant matrix, which also has some pretty nice properties. In fact, you can get the eigenvalues and eigenvectors of that analytically. So in your notes, make sure that's very clear. That's only for periodic, not for Dirichlet. Okay. Sorry, I'm just incredibly thirsty, and apparently I'm the only one in this room who doesn't have a drink. Solve that real quick. Okay. Now, there's two things I hope to accomplish in the last 28 minutes. I want to do a quick rundown of the most often used finite difference approximations. And then I'll use that to explain a good way to handle a Neumann boundary condition. So, the most common finite difference approximations. I tend to cover these in 460 or 560, but that's at least 2 years old knowledge for either of you, 2 or more. So, I guess the same would be true if the other 2 were here. So, first, for the first derivative, there's 3 approximations of interest. Assuming equal spacing, This actually comes directly from a definition of derivative. This is literally f of x plus h minus f of x over h from a definition of derivative. We just don't let h go all the way to 0. This is called a forward difference. Okay. Now, do I have like a proper error analysis in here? I don't believe I do. No, I don't. I'm in less of a mood to digress than I normally am, so I may cover that later. At least in the notes, we pull the error out of thin air, so just this once, because I'm tired. So the error is approximately minus h over 2 uxx at an unknown point. So that's the error formula. And really what that happens is it comes from the next term in the Taylor series. Okay. Because you use the same procedure that I showed earlier, and you set up as many, you decide I'm going to use 2 points. So you can set up 2 equations. But then, so in other words, you get all the values of u, of just plain u to cancel. But then you can have terms involving uxx, and you cannot get them to cancel. So that's why we have this error here. So because we have h to the first power, we say, this is the most important thing, is first order accurate. And we also say that the error is big O of h. All that means is you can bound the error by a constant times h when h gets small enough. Most times that's how we'll describe the error. It's big O of some power of h. We like higher powers of h, it's higher order accurate. Because if h is already small, square it, it's that much smaller still. Okay. So in other words, this is not a great approximation. But it's still useful. We can also go the other way. ui minus 1 over h. So this is the backward difference. Here, it's also first order accurate. In fact, the error term is exactly the other one with the opposite sign. Really, you just replace h by minus h. And you put the two together, you average them. Well, in that case, the ui's have opposite signs, they cancel. ui plus 1 minus ui minus 1 over 2h. That is the centered difference. And the error is minus h squared over 6 times the third derivative. Sorry, I'm going to cheat here. I'm going to look at my book. As soon as you write the thing, it all flies out of your head. I think I have a wrong derivative there. Wait a Oh, no, it's third derivative. Okay. So, yeah, because all the terms involving a second derivative, But you see, in the first order case, those cancel. And I thought I had the second order one here, but okay. Where'd it go? Sorry. It's supposed to be, okay, third derivative over 6 factorial, h times minus h, yeah. Okay, yes, that's the right error term. So, it's order h squared. So, doing about the same amount of computation, you're evaluating u at only 2 points. You get a much more accurate approximation of a derivative. But there's one devil in the details thing. Notice here this error depends on the second derivative. Here the error depends on the third derivative. If your solution to your PDE is not very smooth, like what if the third derivative doesn't exist? Then this could be large. So then you don't really get the accuracy. So that's why for PDEs where the solution can have some troublesome behavior, discontinuity, shocks, etc., this kind of differencing is still used. Like in wave propagation problems, suppose the solution is going to be propagating to the right, use a backward difference because you have information about the solution to your left but not your right. When you try to use a forward difference or a center difference, it goes horrible. That's an example of what's called upwind differencing. You use your knowledge of the direction which the solution is propagating to choose the right kind of differencing approximation. And I've actually tried this, where I tried different difference formulas for the same PDE, and I know versus propagation happening in a certain direction. And yeah, it's immediate. Like you differentiate in the wrong direction where you don't have any knowledge of a solution, and it's wrecked. So that's what we're going to be careful about. Higher order is not always better. If you know your solution is smooth, then yes, it is, but that's not always the case. All right, so that's approximations for a first derivative. And then for a second derivative, well, the one I just derived, now here it's the opposite signs, because before I was approximating minus uxx, but now this is just uxx. And the error is minus h squared over 12, fourth derivative. So it's also called a center difference, but you got to make clear it's for the second derivative, not the first, because it is centered around the point where you want a derivative. So having a symmetry is nice. It causes lower order error terms to cancel. Okay. So I need to show you the ones for first derivative because now I'm going to explain to you how you take into account Neumann boundary conditions. Because the Neumann boundary condition is ux equals something on the boundary. So we need these approximations of ux. So now I'm going to work with a different Poisson's equation problem. So we have minus uxx is equal to f on 0 to 1. Now that part hasn't changed. I'll have a Dirichlet condition on the left side, but I'm not going to say it's 0. It's some given value a that could be non-zero. And at the other end, you can have a Neumann boundary condition. You say ux at 1 is equal to some other value c. So Dirichlet and Neumann. Okay. All right. Okay. I can use the same spatial discretization as before. Xi equal I times h. I'll use equal spacing. So I'm going to have n plus 1 unknowns. All the interior points and the right boundary point. So I have x0, whoops, x1, x2, up to xn. Xn plus 1 is equal to 1. This is 0. Okay. So at these points, it's where u is unknown. It's equal to a over here. So I just need to find u1, u2, up to un plus 1. So I can have n plus 1 equations, and then and my n plus 1 unknowns. Now, the boundary conditions are only going to come into play at a couple of points. So for the most part, I have the same kind of equation as before. So I have, minus ui minus 1 minus 2ui plus ui plus 1 over h squared is equal to fi. So that's my minus uxx is equal to f all over again. For I equals 1, 2, up to n plus 1. So that will take care of most everything. I just have to think about the boundaries now. So, where are my boundary conditions applied? They apply at x0, and they apply at xn plus 1. So, for which equations am I going to have an issue? Like for which values of I am I going to have to do something different? So there's any place where those two boundary points, at 0 or n plus 1, are going to appear. Yeah. So for what value of for what value of I? Yeah, when I equals 1, we're going to have u 0 over here. So that's where the left boundary comes into play. And where are we going to have the right boundary come up? Which values of I?
When I is in.
Yes, when I is n, because this will be n plus 1. What other one? Yeah, because you'll have n plus 1 here, and what's worse, n plus 2 over here. It's like, what? So at those 2 points, we're going to have to deal with the Neumann boundary condition. So now we're just going to focus on those 3 cases, I equals 0, I equals n, and I equals n plus 1. In the last 12 minutes. Now, Dirichlet boundary condition is definitely the easier one to handle. So when I equals 1, I fill in the specific values of I indices. We have minus, okay, so 0 minus 2u1 plus u2 over h squared is equal to f1. So, how do I account for the left boundary condition u of 0 is equal to a? And u1 and u2 will stay, they're unknowns. So what do I do with that u0?
you move to the other side?
Yes, but what can I put in its place? Using a boundary condition that's given.
0.
Well, it's not 0. Yes.
Oh, the given. Yeah.
Yeah. So I can say minus 2u1 plus u2 over h squared is equal to f1. So this term, I move to the other side, so I'll have a plus a over h squared. Okay, so the Dirichlet condition is handled. Okay. Now, at I equals n, and n plus 1, I'll just fill them both in. So I have minus, and I have u n minus 1 minus 2un plus un plus 1 over h squared is equal to fn. I have minus un plus 1 plus un plus 2 over h squared is equal to fn plus 1. Now, so the thing is, anything involving an unknown, like by unknowns are u1 up to un plus 1. I don't have to do anything about those. I can leave them the way they are. So I don't really have to do anything with this equation. This one's okay. I don't have to replace anything. It may involve a boundary point, but it's a boundary point that I've already tagged this unknown. So I mean, we have to make sure, but it's the other equation that we have a real problem.
The n plus 2.
Yeah, because it's not one of our unknowns. It's just outside the domain altogether. Not allowed to use it. So here's what we can do. We have this boundary condition, ux of 1 is equal to c, is approximated this way. Un plus 2 minus un over 2h is equal to c. Why? Because that is ux at point n plus 1. What finite difference formula have I used there? No.
The center.
Yes.
Okay.
Yeah. How you can tell 2h at the bottom and the indices are 2 apart. The one missing index in the middle, n plus 1, is where you're actually taking the derivative. Now, I had other choices. I could have used a forward or backward difference. I could have said like un plus 2 minus un plus 1 over h equals t. But here's why I don't want to do that. Everywhere else, I'm using an approximation like this one. What's the order of accuracy of this one?
Second.
It's second order accurate, the center difference. But the thing is, if I use a forward or backward difference here, that's first order. It would have made the whole solution first order, regardless of this. So it's like a contaminant, if you will, that brings in that disease of low order error that spreads the whole solution and wrecks it. So I need to make sure that any approximation I use, if I want second order accuracy, every approximation I use anywhere be at least second order accurate. So I go ahead and use this center difference. So what that lets me do is it gives me an expression for un plus 2 that I want to get rid of. So it's equal to 2ch plus un. So now I can take that and fill it in here. Okay. So let's see what that looks like. Because ultimately, when I have be able to show you the matrix that resolves, just like in the previous example. So if I go ahead and make that substitution, I'm going to have minus, I'm going to have un minus 2un plus 1 plus un plus 2ch all over h squared is equal to f n plus 1. But now what I do is I combine the like terms. So I have minus out front. So I add these together. So now I have 2un minus 2un plus 1 over h squared. And then this term, 2ch over h squared, I'm going to move that to the other side. It's ultimately a minus over here, so it's a plus over here. 2c over h is what winds up over there. Okay. All right. Any questions on how that came about? So I make sure I actually did it right. Okay, so that is my last equation. And then all the other equations have a similar form as last time. So my matrix, so if A equals F, A is going to be 1 over h squared. I'll fill that in a moment. We also have a vector F, which is going to be all the F values. But I have something to add in the first equation, A over h squared. And then in the very last equation, and then everything else is just an F value, nothing more. As for the matrix, everything's going to be the same as in the previous example, except for the last row. So I have 2's down the diagonal, and I'm going to have ones, minus 1's above, minus 1's below. But now I've got to be more careful about that last row. So I'm going to have, here I have a minus 2. So I will still have a 2 down there. But what am I going to have over here from this equation? Yeah, so if we go over here, so from that equation, so it's equation number n plus 1. So the coefficient of n plus 1, that turned out to be minus 2, so I filled in a 2 down there. So what's the off-diagonal, the only off-diagonal term we can have? The coefficient of that. So you can read it off the equation.
What did you say with the minus 2? Because I was right
well,
when
yeah.
you said that.
So this is equation number n plus 1. So the coefficient of un plus 1 goes on the diagonal, but those indices match. And that turned out to be minus 2 plus 2, so I put a 2 down there. So any other coefficients multiplying u values have to also, from the same equation, also have to go in this row. So what's the other coefficient? No, it has to be something multiplying a u value. All right, one more time. The coefficient of un plus 1 is 2. Well, forget about the 1 over h squared because it's already outside. So I filled that in. So, okay, what's multiplying un plus 1? In equation n plus 1, that's the diagonal entry. So for the rest of row n plus 1, we go back to the same equation. Any coefficient that's multiplying another u value has to appear in a matrix. What's the only other coefficient left? Yes. And it's because it's un to a point directly to the left, goes here, directly to the left. Does that make sense now, kind of? Okay. I know, we're all trained. All right, so that's the matrix. But compared to the previous one, the previous one had a lot of nice properties, and this has most of those properties. What doesn't it have? What's thrown off here because of that last row?
Symmetric.
It's not symmetric, but it turns out we can fix that. What you can do is take this whole last equation and I can multiply it by 1/2. You can always scale an equation, a single equation, by any constant, as long as you do it to both sides. Then that becomes a -1, and it's symmetric again. Now that becomes a 1, but in a symmetric matrix, it doesn't care what you have on the diagonal. So it's on the off diagonal that determines symmetry. Scaling causes those to match, which gives you symmetry. So then using something like Cholesky decomposition or whatever becomes an option again, or a method specific for symmetric matrices. So you just have to remember to scale this too.
Scale what to the right?
The right side. Yeah. It's the forgotten row operation. Everyone talks about, you can add a multiple from one row to another, you can swap rows, but no one talks about scaling a row. Well, except in 326, but that class is lame. But here it actually helps us. But the key was using the center difference, same order of accuracy, to account for the Neumann boundary condition. During my work in the summer at Stennis, I'd be setting up systems like this with different boundary conditions, Dirichlet or Neumann, whatever. But also different discretizations. Like here I used interior points plus the right boundary point, but I was doing something that involved like a staggered grid, like points were moved over by h over 2. So I wanted like a 3 in one of these, so it's kind of weird. But it worked. But yeah, in general, this is how you count these boundary conditions. This point right here, un plus 2, it's called a ghost point. It's a point that's not really part of your problem, but you can still take advantage of it to set up the equations properly in conjunction with the boundary conditions. Okay, well, we've all suffered enough for, a whole week. So, so until Monday, when hopefully we'll have everybody back here.